Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a really interesting area, enhancing large language model reasoning using reward-guided research. It's all about trying to make these things a little less, stochastic parrots.
Stochastic parrots is right. I think we're on the cusp of some serious breakthroughs. I mean, this reward-guided tree search, coupled with the ever-increasing size of these models, .it, feels like we're edging closer to actual AGI.
I'm a little more skeptical. I think we're throwing more and more data and compute at a fundamentally flawed approach. Reward-guided tree search, sure, it might be a slight improvement, but it doesn't address the core issue. These models don't understand anything. They're just really good at pattern matching.
I agree with that to an extent. I think the brute force approach is, brute force. I think AGI is definitely achievable, but we need to start thinking about how to represent space and time. These models are essentially amnesiacs. They can't really integrate information across different spatiotemporal contexts.
Okay, so let's break this down a bit. This paper, Enhancing LLM Reasoning with Reward-Guided Tree Search, basically proposes using a reward function to guide the search for the best reasoning path in a language model. Think of it like this. Instead of just letting the model generate text randomly, you're giving it little nudges, little rewards for taking steps that lead to a more logical or correct answer.
Exactly. And the beauty of it is that it leverages the existing architecture of these LLMs. You're not throwing the baby out with the bathwater. You're just fine-tuning the search process, making it more efficient. It's like giving the model a GPS instead of just letting it wander aimlessly.
But the GPS is still relying on a flawed map. The map, in this case, is the neural network itself, which is trained on vast amounts of text data, but without any real understanding of the underlying concepts or relationships. So, you might get a slightly better route, but you're still going to end up in the wrong city eventually.
And the GPS doesn't know why you want to go to that city. It doesn't understand your intentions or the context of your journey. It's just following the directions. This is where the spatiotemporal understanding comes in. If the model understood the relationships between different places and events, it could reason much more effectively.
So the reward function is key here. The researchers are experimenting with different ways to define what constitutes a good reasoning step. One approach is to use human feedback, where people directly rate the quality of the model's reasoning. Another is to use automated metrics, like checking if the model's answer matches a known correct answer.
And that's where the data comes in, right? The more high-quality data you have to train the reward function, the better it's going to be at guiding the search process. It's a feedback loop, a virtuous cycle. The better the reward function, the better the reasoning. The better the reasoning, the more data you can generate to improve the reward function.
But that data is still just correlations. It's not understanding. Let's say the reward function is trained on a dataset of math problems and solutions. The model might learn to identify patterns in the equations and predict the correct answer, but it won't actually understand the mathematical principles involved. It's just memorizing the answers, essentially.
And it can't generalize. If you give it a problem that's slightly different from anything it's seen before, it's gonna fail. It's like trying to navigate a city using only a street map. You don't have any sense of the overall layout or the relationships between different neighborhoods.
Okay, but let's not dismiss it entirely. I think there's something to be said for using insights from neuroscience to design these reward functions. For example, we know that the brain uses dopamine as a reward signal. Could we design reward functions that mimic the dynamics of dopamine release, rewarding the model for unexpected or novel discoveries?
That's a really interesting idea. It's like trying to reverse engineer the brain's reward system. And if we can crack that code, we could potentially create AI systems that are much more adaptable and resilient.
But even if we perfectly replicate the brain's reward system, we're still just building a sophisticated pattern matching machine. We need to move beyond neural networks and start exploring neuro-symbolic approaches, where we combine the strengths of neural networks with the symbolic reasoning capabilities of classical AI.
Yes, and that's where the spatiotemporal understanding comes in. We need to develop algorithms that can explicitly represent knowledge about space and time and reason about it in a flexible and generalizable way. Imagine an AI that can not only solve a math problem, but also understand the real-world implications of the solution, like how it affects the trajectory of a rocket or the flow of water in a river.
Right, so let's say we're talking about a robot trying to navigate a room. Current systems might use computer vision to identify obstacles and plan a path around them. But a truly intelligent system would understand the affordances of the environment, that a chair can be sat on, a table can be used for support, and so on. It's not just about recognizing objects, it's about understanding how they relate to each other and how they can be used.
And that's where the reward function can come in, right? You could reward the robot for successfully interacting with its environment, for using objects in a way that achieves its goals. It's like teaching a child how to play with toys.
But that's still just reinforcement learning. It's learning by trial and error. A truly intelligent system would be able to reason about the affordances of the environment, to predict the consequences of its actions before it even takes them. It would be able to say, if I push this chair, it will block the doorway without having to actually push the chair and see what happens.
Exactly. It needs to be able to simulate the world in its mind, to create a mental model of the environment and reason about it. This requires a deep understanding of physics, geometry, and other fundamental principles. And it needs to be able to translate between different representations of space and time, from the raw sensor data to the abstract symbolic representations.
So thinking about this in terms of the paper we're discussing, maybe the reward function isn't just about achieving a specific goal, but also about learning these underlying principles. Maybe we can design reward functions that reward the model for building accurate mental models of the world, for making predictions that are consistent with the laws of physics.
But also physics.
That's a fascinating idea. It's like giving the model a curiosity reward for exploring and understanding its environment. And the more it understands, the better it will be at reasoning and solving problems.
But how do you represent those underlying principles in a way that the model can understand? That's the hard part. Neural networks are notoriously bad at representing abstract concepts and logical relationships. That's why I think we need to go back to symbolic AI and explore ways to integrate it with neural networks.
And that's where the spatiotemporal representation comes in. We need to develop symbolic representations that capture the relationships between different objects and events in space and time. For example, we could use a graph structure to represent the connections between different places in a city, or a temporal logic to represent the sequence of events in a story.
Okay, so let's get concrete. Imagine an AI that can play chess. Current chess playing programs are incredibly strong, but they're essentially just brute force search algorithms. They explore millions of possible moves and evaluate them using heuristics. A truly intelligent chess player would understand the strategic principles of the game, like controlling the center of the board or developing their pieces. It would be able to anticipate their opponent's moves and plan accordingly.
And that's where the reward function can come in, right? You could reward the AI for making moves that improve its position, for capturing pieces, and ultimately for winning the game. The DeepMind AlphaZero model used reinforcement learning to achieve superhuman performance in chess, Go, and other games.
But AlphaZero still doesn't understand chess. It's just learned to play it very well through trial and error. It can't explain why a particular move is good or bad. A truly intelligent chess player would be able to articulate the strategic principles behind their moves, to explain their reasoning to a novice player.
Exactly. It needs to be able to represent the game in a more abstract way, to understand the relationships between the pieces and the board. It needs to be able to reason about the consequences of its moves in terms of these abstract relationships. And it needs to be able to translate between different representations of the game, from the raw board position to the abstract strategic concepts.
So maybe we need to design AI systems that can learn both from experience and from explicit instruction. We could train a neural network to recognize patterns in chess games, but then also teach it the strategic principles of the game using symbolic representations. The AI could then use both types of knowledge to make its decisions.
That's a great idea. It's like combining the strengths of deep learning and symbolic AI. And with the ever-increasing amounts of data and compute available, we might finally be able to achieve true AI reasoning.
I'm still not convinced that more data and compute is the answer. I think we need to focus on developing better algorithms that can explicitly represent knowledge and reason about it in a flexible and generalizable way. We need to move beyond the brute force approach of deep learning and start exploring more principled approaches.
And we need to focus on spatiotemporal understanding. We need to develop algorithms that can represent space and time in a way that allows them to reason about the relationships between different objects and events. This is essential for achieving true AGI.
So let's talk about limitations. The paper itself acknowledges that reward-guided tree search can be computationally expensive, especially for complex reasoning tasks. You're essentially exploring a massive search space, and the reward function needs to be very accurate to guide the search effectively.
But that's where Moore's law comes in. As computers get faster and cheaper, we'll be able to explore even larger search spaces and train even more accurate reward functions. The computational cost is a temporary obstacle, not a fundamental limitation.
But Moore's law is slowing down. And even if computers continue to get faster, we're still going to hit a wall eventually. The complexity of the search space grows exponentially, while the computational power grows linearly. We need to find more efficient algorithms that can prune the search space more effectively.
And that's where the spatiotemporal understanding comes in. If the AI understands the underlying structure of the problem, it can prune the search space much more effectively. It doesn't have to explore every possible move. It can focus on the moves that are most likely to lead to a solution.
Another limitation is the potential for bias in the reward function. If the reward function is trained on biased data, the AI will learn to make biased decisions. This is a major concern in areas like criminal justice and healthcare, where AI is increasingly being used to make important decisions.
That's a valid point. We need to be very careful about the data we use to train these systems and ensure that it's representative of the population as a whole. We also need to develop techniques for detecting and mitigating bias in the reward function.
But even with careful data selection, it's still difficult to eliminate bias entirely. The problem is that the reward function is learning from human behavior, and human behavior is inherently biased. We need to find ways to incorporate ethical considerations into the design of AI systems to ensure that they're making decisions that are fair and just.
And that's where the spatiotemporal understanding comes in. If the AI understands the social and historical context of the problem, it can make more informed decisions. It can recognize that certain groups have been historically disadvantaged and take that into account when making decisions.
Okay, so let's think about future research directions. From my perspective, I'm really interested in exploring the connection between neuroscience and AI. How can we leverage insights from the brain to design more intelligent and adaptable AI systems? I'm particularly interested in the role of neural oscillations in integrating different aspects of information. Could we use this insight to develop more sophisticated tree search strategies?
I think we need to move beyond deep learning and start exploring neuro-symbolic approaches. We need to develop algorithms that can explicitly represent knowledge and reason about it in a flexible and generalizable way. I'm particularly interested in developing AI systems that can explain their reasoning, so that we can understand why they're making the decisions they're making. If reward-guided tree search is the most effective method for improving large language models, what fundamental principles of logic and symbolic representation are we neglecting by relying so heavily on data-driven approaches?
I think we need to focus on spatiotemporal understanding. We need to develop algorithms that can represent space and time in a way that allows them to reason about the relationships between different objects and events. I'm particularly interested in developing AI systems that can translate between different coordinate systems so that they can understand the world from multiple perspectives. If AGI is to be more than pattern recognition, it needs a way to understand the underlying relationships between different spatial and temporal representations.
So, to wrap up, this paper on reward-guided tree search offers a promising step towards enhancing the reasoning abilities of large language models. It's not a silver bullet, and it certainly doesn't solve the fundamental problem of understanding, but it's a valuable contribution to the field. And as we've discussed, there are many exciting avenues for future research, from neuroscience-inspired reward functions to neuro-symbolic approaches and spatiotemporal reasoning.
I agree. I think we're on the right track. And with continued investment in research and development, I'm confident that we'll achieve AGI within our lifetime.
I'm not so sure. I think we still have a long way to go, but I'm hopeful that we can make progress towards more intelligent and ethical AI systems.
I'm optimistic that we can achieve AGI, but I think it will require a fundamental shift in our approach. We need to move beyond brute force methods and start thinking about how to represent knowledge and reason about it in a more flexible and generalizable way.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. We hope you found this discussion informative and thought-provoking. Until next time.